Well, welcome to another exciting digital design class. I hope everyone can hear me okay. Just click yes if you can hear me. Got a few. Yep, looks like a few people are clicking. Thank you. Sounds good. I'm going to open up my little chat window here. Yeah, somebody said, yep, we can hear you. That's great. First order of business, we had a homework that was due yesterday evening. And I was wondering if anybody had any questions about yesterday's homework. Nope, no questions. All right. We also had a video to take a look at. Did everybody have a chance to look at the video? And would you did you have any questions about it, or would you like me to review it? This is the one where we were synthesizing a counter that counts to 3. We kind of did that in the last class. I'm hoping that people are starting to get it. And it doesn't seem like anybody has any questions. So that's a case of what's called forward synthesis. In forward synthesis, we give you a high-level spec, and then we ask you to try and synthesize the design and implementation of a circuit that will realize that specification. There's another skill which you need to know, and this is called reverse engineering. And in reverse engineering, you are given a circuit, and then you want to find the high-level spec. And so at that point, you are going to have an opportunity to essentially do what you did before, only in reverse, if that makes any sense. So what we're going to do here is we're going to start with this basic idea that you're given a circuit. Okay? And we're going to see this in homework number 9. And it's quite a common thing to see in terms of, well, I'll say in terms of tests and homeworks. We'll see these sorts of things before. I hear somebody has got the music playing in the background. I'm going to mute you. Hope you don't mind. So that's yeah, just got to watch that when you're starting to join. You want to make sure you don't have your how you say microphone on. So anyway, let's start with a simple. I'm going to start with a simple one. Suppose I give you a toggle flip-flop, and its output is Q and Q prime. And then we give you another toggle flip-flop, and its output is Q and Q prime. And what we'll do is we'll take this and we'll run it right into here, and we'll take this one and we'll put a 1 in there. And that's a real simple sort of first example. What does it do, and how do I approach this problem? Any ideas? I mean, here we are looking at this really simple thing. It doesn't even have any gates in it. It's just a couple of toggle flip-flops. I wired them up, and that's it. What does it do? And how can I tell? So first question is how can I tell? We've got to go through and do an analysis. And the analysis requires that we label the flip-flops so they're distinct. And so what I'll do is I'll erase the Qs, and I'll give them variable names.
Hello.
Hello? Yes?
Hi, just saying hello.
Oh, okay. So then we're going to put in variable name A and A prime. B and B prime. And now we can do a little bit more of an analysis. We see that there is no input to the system other than its state variables, its present state, and its next state. And so what we'll do is we'll attempt to write out all possible present states using A and B, and we'll just count in binary. This is a little 2-bit device because there's only 2 flip-flops involved, and there's no input, so we don't need to have the input, which would be shown on the left, for example, if it was an up-down something or other. And now the next state, we don't know, but what we do know is we know the inputs, T sub A and T sub B. That we know, and we know that because of how things are wired up. And we see T sub A is equal to B prime. So if we take B and we invert it, that should be equal to T sub A. So this will be 1, 0, 1, 0. Everybody can sort of see that, I hope. B prime is hooked to T sub A, therefore T sub A must be equal to B inverse. Let's take a look at T sub B. T sub B is equal to 1. That's easy, we'll make that 1. 1, 1, 1, 1. Now, given, let's change colors just because that's a fancy thing to do. Given the present state and the input to the flip-flop, which is shown in the green box, I should be able to obtain the next state as A plus B plus, right? And how do we do that? Right? One thing we know about flip-flops is we know how they operate when we know the present state and we know the input. Now, A plus is going to be equal to A inverted if T sub A is equal to 1. In other words, T sub A says during the next state, we're going to invert. It's a toggle flip-flop. So if it's a 1, it's going to toggle during the next clock cycle. So if A is a 0 and we put in a 1, next clock cycle, it's going to be a 1 because it flips from 0 to 1. And then T sub B, if it's a 0, it's got to flip to a 1. And if it's, if it's a 1, it's got to flip a 0 to a 1. So that's a basic idea. And using this 0 in here, that's a hold state, so we stay 0. Here's a 1, so we're going to flip the 1 and make it into a 0. And in fact, what's going to happen is this is going to go 1, 0, 1, 0. And the 1 over in here is going to flip to a 0, and the 1 over here is going to remain in its present state. And now I have the present state, and I got the next state. Normally I'd write it on the top, but I got a little jammed up here because my tablet is too little. So now I can say that it's possible for me to write the present state next state diagram. So if I number the present state in decimal, I can write that 0 will transition to 3. That's interesting. And then 2 will transition to 0. And then it says here, actually that's 1 transitions to 0. Let's get an eraser here. Oh no, this says, yeah, 1 transitions to 0, 2 transitions to 1, 3 transitions to 2. And now it goes 3, 2, 1, 0. So this is a countdown timer. That's what our countdown circuit. And we can do that through a simple analysis phase, and this is called reverse engineering. And we got that because we understand how flip-flops behave. We can use a couple of things that can help us. If we know Q and we know T, we should be able to get Q plus, and we call that the excitation table for the toggle flip-flop. And so what we say is that this here is a hold state, and this is the toggle state. And in the hold state, we maintain the state of the flip-flop, so we go from 0 to 1. In the toggle state, we flip the state, so that means it goes 1, 0. And so that basic excitation rule is all we need to know in order to be able to extract information from the inputs to the toggle flip-flop and the present state. And that is an example of reverse engineering. And you're going to see an example just like that in homework 8. So what do you think of that? Does that kind of make sense to people? And you can say no if you want to. So I'm getting a couple of check boxes. Are there any questions about this? Because I'm going to do another example, but this time it's going to be more complicated. Is that all right? You guys you're a quiet bunch. Yep. Okay. So we're moving on. Moving on to the next example. Let's do another one. I think I can do this one here. Let's do this one. I'm going to put in an exclusive OR whose input is A, B, and U. And it goes into a D flip-flop, D sub A, whose output is A prime. And then I'm going to get another flip-flop, D sub B, whose output is B and B prime, and whose input is B prime. So now, how do I do the analysis on that? So the big question is, what does it do? We were going through homework 8, right? No, I asked if there were questions about homework 8. Right now, I'm working on the next homework assignment, which is homework 9. Did you want to go through homework 8? We can do that. I'm doing a reverse engineering here. Okay, it's fine. Good. So my reverse engineering analysis requires that I start with the input U, because U is now a new, we treat it as though it were a state variable, but it's really not. Then we have A and B, and I put U in the front because U is going to change the mode of our system. And so now I'll write out all possible combinations of input and present state. And then I want to figure out how to get A exclusive OR B exclusive OR U for my input D sub A. So that big exclusive OR has to be somehow computed. So this is 0, here's a 1, here's a 1, that's a 0. Here's a 1, here's a 0, here's a 0. Now we got a 1. And now we're going to do D sub B, and our analysis says D sub B equals B prime. So we just invert B, and we get 1, 0, 1, 0, 1, 0, 1, 0. Now, because we know how D flip-flops work, we gotta mute somebody out there. Yeah, I'm leaving it to you guys to mute and unmute yourselves, because if you have a question, you can just pipe right in and interrupt me, and that's totally okay. So now I'm going to show the next state. And what do we know about D flip-flops? Well, we know D flip-flops have an input D, and we know they have a present state Q. And we also know that the excitation table for the D flip-flop requires that its next state will be equal to the input. Which question is this? This is just a general idea of how to solve reverse engineering problems. I'm going to work up to some of the questions in homework number 9, just as soon as I can get past some of the introductory preliminaries on how to do a reverse engineering problem. So I don't know if you're anxious to get to the homework or not, but I'm taking it easy on this one because I feel it's very important to do simple first examples and then work up to the more complex ones so that you can see where I'm coming from when I start to get to the more complicated ones. Because before I go to a JK flip-flop, I want to do T flip-flops and D flip-flops. Then I'm going to do a JK flip-flop actually out of the homework. So yeah, sorry if you're lost. I know it's okay. Don't worry. You know, everybody should be able to ask questions, and don't be sorry. It's totally fine. It's really too quiet out there. I appreciate the questions. So thank you for the question. Maybe I wasn't clear on my pedagogy. I'm starting with simple first examples. Then I'm going to work up to the homework. So for my next state, I know from my, I'm going to put a little color in there for no reason. This is my excitation table. Exciting, right? Excited, my excitation table. And so what I'm going to do with my excitation table is I'm going to use this and say, aha, I now know how T flip-flops behave. Based on their input, that's what the next state will be. It won't always be so simple, but we'll do it this time. So the next state is going to be just a copy of whatever the input is on the D flip-flop. Okay, so now we can essentially see the method to my madness of grouping the input on the most significant bit because it's changed the basic behavior of the flip-flop. So when U is equal to 0, we go to a 1. And so now we have state 0, and here's state 1. And when there's a 0, we go to a 1. And when there's a 1, we go to 2. Okay. And when there's a 2, we go to 3. And then when there's a 3, we go back to 0. So you should recognize this. We've seen it before, but that's okay. Now here's a 1. If we're in 0, it goes to 2. No, it goes to 3. That's where it goes. And then if there's a 1, it goes to 0. And then if there's a 2, it goes to 1. And then if there's a 3, it goes to 2. And that is the answer to the question, what does it do? And the answer is it's an up-down counter. Now, had we been given the state diagram, it would have been very possible for us to synthesize this circuit if we were told that we wanted to implement it with D flip-flops. But let's do the same thing. Let's now go and take this new high-level description of an up-down counter, and now let's turn it into a new implementation with a difference. And the difference is we're going to re-implement the whole thing with JK flip-flops. So now I've got a new present state, next state table with input U, A, and B. And in this case, we're going to be doing the up count. And here, we're going to do the down count. So these are two different modes for our up-down counter. So this part is the same, right? This is the spec. And then here comes A plus and B plus, right? And now we can write out that if we're doing an up counter, 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes back to 0. If we're starting with 3, we go 3, 2, 1, 0, and then back to 3. Right? So this is the spec, but now we're going to change it around a little bit. Now we're going to do the same exact thing with a difference. And the difference is we'll have an input for a JK flip-flop with the A bit and an input for a JK flip-flop with the B bit. In fact, what we can do, it says save to photo albums, I don't know why, with the B bit. Let's erase that and make it nice. No. How do I make the eraser? Oh, okay. With the B bit. Yeah. Yeah, I need a K. That's it. Yay. He did it. Yay. So what's missing from my little remapped excitation table? And the answer is I need to know something about JK flip-flops. J, K, Q, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Whoa, I don't have time. I don't have space. Darn it. What's going on here? You know, if this were the graph paper, I wouldn't be having this problem. Tell you what we're going to do. Let's get an eraser. That's it. We'll just do it right up here in the corner. I'm changing to green. J, K, Q, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0. And then write out Q plus. And how does this behave? Well, let's take a look. In this mode, we're in the hold state. In this mode, we're in the set state. Sorry, the reset state. In this mode, we're in the set state. In this mode, we're in the toggle state. Based on that, I can see if we're in the hold state, we maintain Q. If we're in the reset state, we clear. If we're in the set state, we go to set. If we're in the toggle state, we flip the bit. So now let's take a look at what JK will be. If you want to go from 0 to 0, what should it be based on this? And the answer is we kind of don't know. We still need to know something or other about where the don't cares are going to be. And the remapped excitation table for the don't cares on the flip-flop come at least in part because there's multiple ways to have a transition from 0 to 0. So we go back through our little mapping in here, and we can say there's two ways to do a transition from 0 to 0. And when we see that, we say, okay, it's a don't care on X. It's a don't care on K, but it's a do care on J. So this would come out to be 0X for JK when a 0, 0 transition occurs. Excuse me while I turn off the ringer. There. I'll just keep the phone off the hook. So there's two ways also to go from 1 to 1. And we can see that it's a don't care on J, but it's a do care on K. And K actually has to be 0, and J is going to be equal to X. So it's going to be X 0. And so if you want to go from 1 to 1, and you can do this with the Q and the Q plus to get your excitation table, you write 0, 0, 0, 1, 1, 0, 1, 1. Going from 0 to 0, we can see that JK has to be 0x. Going from 1 to 1, we can see JK has to be x0. Using the similar analysis, we can obtain the remapped excitation table inputs for JK, and this will come out to be 1x, and this will be x1. And you need this, right? This is so important. This was the first page of the instructions in homework 8. And this is the remapped excitation table for the JK flip-flop. And so what you want to do now is to say, well, to go from 0 to 0, I need 0x. To go from 0 to 1, right, I need 1x. To go from 0 to 1, I got to have 1x. To go from 1 to 0, it's supposed to be x1. And you fill out the remapped excitation table just like that. And you kind of have to be neat about it, maybe more neat than I am because I'm trying to do this on an iPad. So to go from 0 to 1, I can see I need 1x. To go from 1 to 0, I have to have x1. And that's going to be x1. And that's going to be x1, because that's 1 to 0. Here's 0 to 0, so it's going to be 0x.
Professor, can you tell us which digits are we looking at to determine this?
Sure, let me number the K-map here, or number the truth table. 0, 1, 2, 3, 4, and 5. So let's try and do one real slow here. I see here I'm going from 1 to 0. So I take this yellow line in here. 1 to 0 is a transition. So I look over here and I say a 1 to 0 transition can give me an input for jk, which is equal to x1. So I go in over here and I write x1 right there. What do you think of that? So you gotta say, here's the transition I want, 0, 1. To get 0, 1, I write in 1x. Here's a transition I want 1, 1. To get the 1, 1 transition, I write in x0. And here's another transition from 1 to 0. And to go from 1 to 0, I write in x1. And you need these don't cares because they're going to simplify your K-maps. So that begs the question, what do we do now? And the answer is, if you want a minimal form for the inputs on J, K, JB, and KB, you can either do it by routine inspection, maybe, or probably going to have to write a K-map. So what I would do in a case like this is make a little space for myself, because I need some K-maps. And let's see if we can get a couple or 3 K-maps in here. We need 4. We need 4 3-variable K-maps. And I'll try and start with J sub A. So we'll put in AB and then U. We'll change our color. And then I'm going to read off the numbers. I got a 1 in row 1. I got don't cares in 2, 3, 4, 6, and 7. 2, 3, 4, 6, and 7. And so now I got to loop my K-map. And that's really the only loop I got. So now I can write J sub A is equal to, and I'll write out A prime, J A prime. And now I got to do the same thing for my K, right? K is going to come out to some other number. We don't know what it is yet. So let's see if we can get that. So this will be another K-map. I didn't leave myself enough room, did I? Ah. And so, yeah, did it again. Darn it. 0, 0, 0, 1, 1, 1, 1, 0. See if we can do this. We're really packing it into this little area here. 0, 1, 2, 3, 4, 5, 6, 7. And now what we'll do is take a look at K sub A, and this will be K sub A equals, and I got 1 in elements 3, 4, and 6. I got don't cares in elements 0, 1, 5. So now I got to do my looping, and that's a good loop right there, and that's a good loop right there. So that says that's supposed to be A and B up in here. So that says I got A prime J. So let's write J A prime, or, and now it's going to be A J prime, or A J. Yeah, it's J prime A. J prime A. And now I got to do the same thing for J sub B. I hate squeaking in K-maps like this. So I'm going to go down to the where there's a little bit more room, down over in here. And this will be A and B. This will be U. This is supposed to be a U, isn't it? Here, let's fix that. It's so hard to write with the stinking iPad, you know? Let's see if we can get this to work. There you go. Did it. So now 0, 0, 0, 1, 1, 1, 1, 0. Tiny little K-maps. 0, 1, 2, 3, 4, 5, 6, 7. Always number your K-maps. And now we're going to have a 1 in 0, 2, and 6. And we're going to have don't cares. Actually, the whole thing can be 1. That's trivial. Right? Look at this. And just say J sub B equals 1. And K sub B is equal to 1. Oh, that's good. I like that. I don't have to do K-maps now. So now I can write out the circuit J sub A, K sub A prime, and J sub A is equal to U A prime, handed together. And then K sub A is equal to U exclusive or A. And now J sub B, K sub B can be wired together and set equal to 1. And that'll give me B prime. And that should give me my new up-down circuit. This time, it looks like quite a different implementation from last time, right? Why? Because what we've got is a totally different flip-flop set. Now, the question is, which one would you prefer to use? The one that has 3 input exclusive ORs, or the one with an AND gate and an exclusive OR? If the answer is it doesn't really matter, then you might want to go back to the simpler design. But at least with this one, you've got a basic idea of how to do the forward synthesis with the JK flip-flop. And it all starts with an excitation table, as well as the, let's say, present state, next state specification, which is really what's over here on the left. So that's your spec right there. I'll just write spec. So what do you think of that? Your questions?
So, yeah, for the JB and KB, can't we just replace that with just an input of 1?
Yeah, that's what I did. If you look at the lower right corner over here in the red box, you have JB, KB equal to 1. So when I saw this, I started down the path of doing a K-map, but I said, hey, wait a minute. It's all 1s and don't care, so the whole thing is 1. And the same thing happened with KB. So I just wired them together and set it equal to 1. And that becomes a toggle flip-flop with the input set equal to 1. So it's always flipping from 0 to 1.
Oh, so this is always flipping.
Always, yeah. That you know what you have here is a buzzer.
Toggle flip-flop?
Yeah, it's a buzzer. It's just going to keep flipping. And if you look at the least significant bit on B plus, that's what it does. It just keeps flipping from 1 to 0, 1 to 0, 1 to 0, 1 to 0. That's all it does. So the job of B is to just keep flipping. And that's why we have replaced essentially the JK flip-flop with the toggle flip-flop whose input is 1. In fact, you cannot commercially buy toggle flip-flops. What you do is you buy JK flip-flops and you wire them together, and that makes a toggle flip-flop. You wire J and K together, and you got a toggle flip-flop. That's what they do, and you can see why that's true, right? Because if you have any instance where both inputs are equal to 1, and then we kind of ran through this, but then I erased it, it goes into a toggle mode. That's why toggle flip-flops are kind of cool. Because you can turn, I'm sorry, JK flip-flops are cool because you can turn them into toggle flip-flops. Any other questions? So why don't we try one of the questions out of homework 9 and see how we can do with that now that we've got a kind of a good feel for how to do our forward and reverse synthesis. Because I think that, we're ready for it now.
Let's do number 1.
Well, I was going to do a harder one. I was going to do number 8, which is a reverse synthesis question.
That's fine.
Yeah. So this is kind of what we had before when we did it with D flip-flops. And now you can see it's a totally different implementation when you do it with JK flip-flops. So now I'm going to do another sort of little analysis here. Let's go back to a circuit diagram. So given, and I'll write J sub A, K sub A, and now this is number 8 out of homework 9. What we're going to do is we're going to wire this up to J sub B, K sub B, and we're going to have an output A and A prime, B and B prime. And now what I want to do is I want to take the output from A and run it into the clock input on my J sub B. And in fact, before I even do that, what I'll do is I will put in a little inverter. And then I'll run it in to the clock input on my J sub B, K sub B. And then what I'd like to do is take the input for K and, let's see, K sub A and K sub B, wire them together and make that a 1. That'll be the high state. And then I'm going to take the input in here, wire it together, and make that a 1. So we'll turn that into a high state. So that's interesting. What does that do?
Isn't that just a clock?
Well, if this has an input which is a clock, right? What is the output going to be? Well, we can tell what the first thing is going to do because it's got 2 1s going in. So that's the moral equivalent of a toggle flip-flop with a 1. So that's going to generate an output that goes kind of like this. But then what happens is it runs through an inverter. So that's the moral equivalent of having A prime come out, which is going to look kind of like this. And so now you got that going into the clock input of the next stage, right? That's the clock. That's not going into the input A and B. So it acts like a toggle flip-flop, but it flips at exactly 1/2 of the frequency of the input. So what that does is it creates a new clock with a 50% duty cycle and exactly half the frequency of the input signal. So what that does to you, it's going to look like this: 0, 0, 0, 1. This will be the A. This will be the B. That's the slower one. And now it's going to flip 1, 0, 1, 1. And that is going to then turn around and go back to 0, 0. So basically, you built a counter without any additional logic at all. And the reason why is because you're using this with one gate of propagation delay, and then you do the inversion and then run it into your counter. And so that gives you a flip-flop, let's say 2 cascaded toggle flip-flops, and this creates an interesting kind of counter called a ripple counter. And you can find these in the 74161. It's kind of counter that can go up or down. And these ripple counters are quite common. And so his counter speed is limited only by the propagation delay through the JK flip-flop. So your rate, right, is limited by propagation delay of each flip-flop. Each flip-flop. And that's the answer to question 8. I think this bears examination. I think we need to do another example of reverse engineering. So let's do one. This time I'm going to do a 3-bit example with toggle flip-flops. This will be question 11. So we've got an opportunity here to try and learn something about how to do our reverse engineering. So let's start with the basic idea that we're given a circuit. This is number 11 now from homework number 9. Somebody's got their microphone on. You got a question? What do you think of this iPad? Is it all right? I'm sort of trying to use the iPad whiteboard instead of the camera. I'm not convinced it's better because as sloppy as my handwriting is, it makes
You need a bigger iPad.
I know. That's what I'm thinking. I ordered a tablet, an actual writing tablet, a Wacom Bamboo.
Nice.
So you like this better than the camera? That's good. All right. So we'll continue doing that. All right. So what we'll do here is we'll get let's see now, A to drive this OR gate and this OR gate down in here, and maybe this OR gate down over here. And then what we'll do is we'll get B and C And we'll run them into an exclusive OR. And B will be used to drive this OR gate from here. I'm going to change colors. And we're going to take the output and run it into an inverter. And the inverter will be used in here. And then we're going to take the output before the inverter. And let's change colors again. We'll use it over from here. And let's see, what else do we need to know? I think that's it. All right, so what does it do? And this is question 11. And it's a question that I've selected from various tests as well that we've seen in the past. So what we have here is a finite state machine circuit. It's not a diagram, it's a circuit. We want the finite state machine diagram, but we don't have that. All we have is a circuit. So how do we do the analysis here? There's no inputs. Oops. Why doesn't this erase? It doesn't erase. Save to photo albums. Stop that. Okay, so let's take a look. I'm going to write down some equations. T sub A. Let's see if I can do this properly. T sub A equals. Now it looks like it's equal to B exclusive OR C, ORed with A. So A or B exclusive OR C. T sub B is equal to A ORed with B. A or B. T sub C is equal to A ORed with B exclusive NOR C. Does everybody kind of see that? So at this point now, I can write out a present state, A, B, C. I can write out T sub A, T sub B, and T sub C. And I know T sub A is going to be A. So there's A. Let's sort of put in a line. Here's A. Or B exclusive OR C. So we'll do the exclusive OR between B and C. That's 0, 1, 1, 0. And T sub B is going to be A or B. So A is here. Or B. And T sub C is going to be A. Or B exclusive NOR C. So if this is B exclusive OR C, then the opposite, wait a minute now. That should have been a 0, shouldn't it? B exclusive OR C. T sub B is supposed to be A or B exclusive OR C. That's a 0. Got to keep me honest here. B exclusive OR C over in here is supposed to be a 1. There. B exclusive OR C. So now I'm going to invert T sub B and get 0, 0, 1. Now I've got my toggle flip-flop inputs. I can come up with A plus, B plus, and C plus. How? Can you guys do that? How do we do that? Well, I know that if the input is a 1, I'm going to flip a bit. If the input's a 0, I'm in a hold state. So 0, 0, 0 with the input 0, 0, 1 is going to become 0, 0, 1. Here we have 0 and 0 with two 1s coming in, and then a 0, so that's a 1. And so now I'm going to have 1, 1, 0. Sorry, 1, 1, 1, all 1s. Then over here I got a flipped bit, another flipped bit, and a bit that remains constant. And finally, I have a bit that remains constant, a bit that flips. Oh, the input's 0, so it stays 1. And here a bit, this bit is going to flip, so that goes to 0. So let's just make sure I got this right. 0 is on input, starts with 0, ends with 0. Here 0 is an input, starts with a 1, it ends with a 1 because it's a hold state. Here there's a 1 on input, so you take the 1 and you flip it to a 0. So that's correct. Why is TB in the second line 1? T sub B in the second line of 1, it should be a 0, right? T sub B is equal to A or B. A or B. Yes, it should be a 0. I don't know why I thought it was supposed to be exclusive or. A or B. And then that should be A or B. A or B. Yep, that's correct. So then C is supposed to be T sub C. I hope I got this right. Gee, how much error did I make here? T sub C is supposed to be equal to A, and or B exclusive or C inverted. So that's a 1. That's going to be a 0. That's going to be a 0. 1 exclusive or with 1 is going to be 0 and inverted, and it's a 1. So 1, 0, 0. Let's just make sure this is correct. One, 0, 0, 1. So that's correct. So now let me just go through this and make sure I got it right. So T sub C's input is going to cause this to flip. Here's a 0, it remains a 1. Here's a 0, that remains a 0. Here's a 1, it takes the 1 and turns it into a 0. Here's a 1. These are all 1, so it's going to keep flipping. 1, 0, 1, 0. These are all 1s, so that's going to be flipped. 0, sorry. 1, 1, 0, 0. And then this is going to flip every one of the 1s to a 0. And now, if I've got this right, I should be able to extract the, it says here, the second line for B plus should be a 0. The second line for B plus should be a 0. Let's see if that's true. Got a 0 on input and a 0. Yes, you're correct. Thank you. Any other blemishes in my B plus on the second line should be, I fixed it. Thank you. Thank you for keeping me honest. What other errors are there, if any? Looks good, right? All right, let's number our truth table. 0. I'm gonna number it in black. Here, let's number it in black. TB on the fourth line should be a 1. TB on the fourth line, 1, 2, 3, 4. It looks like a 1, but it's not. And TB on the fourth line. TB is A or B. A or B is 1. It says the 3, the third line. So A or B is equal to 1. So that's a 1, right? That's supposed to be a 1. Then B plus should be a 0. Yes, it should. That is true. Any other errors? Working on this iPad is not good for me. So there you have it. You want to do your analysis now. 0 goes to a 1. 1 goes to a 5. 2 goes to a 4. 3 goes to a 0. 4 goes to 7. 5 goes to 7. 6 goes to 7. And 7 goes to 7. And that is a finite state machine, unlike any that you've seen before. But it allows you to now answer some of the questions that we have here in the finite state machine diagram. Now, I thought 7 goes to 0. I don't know why I thought 7 was going to 7. I think I'm reading off from the T sub A section. Here's 7, here's 0. So that's not correct. I'm reading the wrong section. 7 goes to 0. There we go. 6 goes to 1. Yeah, I'm going to do this again. Boo hiss. Let's do it again, only this time I'm going to write out the actual numbers on the right-hand side. So this is a 1, 5, 4, 0, 3, 2, 1, and 0. So now I have, there. It's better if you write out the numbers in decimal so you don't have to try and convert from binary to decimal in your head and read the wrong columns. So it's 0 goes to 1, 1 goes to 5, 5 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to 0, 7 goes to 0, and 6 goes to 1. And so now you've got the opportunity to rewrite the whole thing in binary if you like, and you'll be able to match it against the answer in the question number 11. So that takes quite a bit of work. I guess the key to making it easy is writing it in decimal on the present state and the next state. So this is the present state. This is the next state. And when you write it out in decimal, it makes it much easier, right? Because otherwise what happens, and this is just what happened to me, you read off from the wrong columns. And if you do that, it looks like 4 is going to 7 instead of 4 going to 3 because you're reading from the wrong place. What do you think? That was just one of the answers in homework number 9. Homework 9. So I've got a few questions that are hard like that. I think it's very good if we keep track of which questions we've done. So far we've done. Well, let's take a look.
8 and 11.
Yeah, 8 and 11. So it takes a little while to work through these problems, but I think it's a good exercise for you, and you should definitely try and do some of them on your own. Let's see if we can do another one. I am looking at some of these questions here and trying to figure out which one you want to do next. I think what we'll do is we'll try and attack some of the harder problems. So here's one called the gray code. Gray code. Let's take a look and see how gray code can be derived. I'm going to try and derive a 3-bit gray code for you. Gray code is due to a researcher over at AT&T Bell Labs called Frank Gray. And what he wanted to do was come up with a way to count so there would be only 1 bit of difference as you went from one binary number to the next. So let's try this. Suppose you wanted to go and snake through the K-map in the following manner. So we'll start here. We're going to end up there. This is a homework problem, and it is also an example. This is homework number 12. I'm sorry, question number 12 out of homework number 9. So we start with this idea that there's this code that's going to represent a series of bit vectors that are different by 1 bit. And we start by doing this with K-maps, and I call this little lecture Fun with K-maps, because K-maps are very fun, aren't they? Yes, yes, Professor Line, very fun. So what happens if you write out 0, 1, 2, 3, 0, 1, sorry, counting, 0, 1, 3, 2, 6, 7, 5, 4, because that's the order in which things are appearing if you snake through the K-map as shown. Write it out in binary, A, B, and C. I will change colors, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. So what are we looking at here? The difference between row 0 and row 1 is just 1 bit, the least significant bit. From row 1 to row 3, we have the middle significant bit. From row 2 to row 6, it's the most significant bit. From row 7 to row 6 is only the least significant bit. In other words, as we go from one row to the next, we see there's only 1 bit of difference. And now it should be possible to devise a counter using, let's try toggle flip-flops. So what we'll do first is we'll write A plus, B plus, C plus. So this is a counter, unlike any counter you may have seen before. It has a very funny looking count. It goes 0, 1, 3, 2, 6, 7, 5, 4, and then returns to the beginning. So from 0, we go to 1. From 1, we go to 3. From 3, we go to 2. From 2, we go to 6. From 6, we go to 7. From 7, we go to 5. And from 5, we go to 4. And then from 4, we go back to 0. And now we can devise inputs for our toggle flip-flops. Anybody lost on this? Just give me a yes if you're following along, please. Is it clear? Yes, so far? Got a few yeses in here. Okay, so it's you're getting it. That's good. That's good. I just need a little feedback here, some encouragement. For some reason, there's a yeah, I want that. So let's see if we can't figure out how much time do I have? 10 minutes? Okay. What T sub A, T sub B, and T sub C should be. We are in question 12 right now. So A is not changing. B is not changing. C is changing. A is not changing. B is changing. C is not changing. So we have no change and change in the least significant bit. Here we have change in the least significant bit. Here we have change in the least significant bit. Here we have change in only one bit. Here we have change in the least significant bit. And here we have change in only the most significant bit. Should line 4 of A plus B plus C plus B 1, 1, 0? Let's see. Line 4. I'm going to number these 0, 1, 2, 3, 4, 5, 6, and 7. So line 4 looks like the least significant bit should be a 1. Oh, so line 3. Okay, so line 3 should be, let's see now. We want, this is not changing. This is not changing. The least significant bit should be a 1, right? Because that's a 1. So I think it's correct. Unless you feel, yes?
No, I think he means the next stage columns. They are, so I assume for the next stage would be whatever the next stage is for ABC, right?
Yeah, so 0
Yeah.
goes to 1, 1 goes to 3,
Mm-hmm.
3 goes to 2, 2 goes to 6. This
Yeah,
should be 6.
I think that's the blemish.
1, 1, 0. Okay, so if that's going to be a 6, then this has to change. And so that says that this is going to flip, that's going to flip, and the other one will remain the same. So it's going to go 1, 0, 0, 1, 0, 0. Right? I think that's correct now. Thank you. Thank you for that. So from 2, we want to go to 6. From 6, we want to go to 7. From 7, we want to go to 5. From 5, we want to go to 4. From 4, we go back to 0. I think we've got it right now. So let's take a look at what we need to do to implement T sub A, T sub B, and T sub C. I think we're going to need a K-map. My K-map senses are tingling. How am I doing on time? Good. Okay, so let's grab, looks like 3 and 7. Oops. Are going to be a 1. And so what that tells me is T sub A, actually you can write it over here, T sub A is equal to AC. And we'll do it again.
Angels.
It says here line 4 of A plus B should be 1, 1, 0. And then, I'm sorry, is there a question? 0, 1, 2, 3, 4, 5, 6, 7. Okay. Let's change the color. And now what we'll do is we're going to try T sub B. And T sub B is going to be a 1 for 1 and 5. 1 and 5. So we're going to loop this way. And then T sub B is going to be equal to, let's see now, A C prime, I think. That's not too bad. And now we got to do T sub C. And that's going to be a 1 for, looks like 0, 2, 4, and 6. And so that's going to give me a single loop that's equal to A prime. So T sub C equals A prime. And I could draw this circuit with relative ease, and it gives me an answer which we can now use to look up the answer for question number 12. And I think that is all we have time for today. I'm just going to make a little note to indicate that this was done in section 1. That was question 12. We did, I think we did question 11 as well, didn't we? Question 11.
That would be true.
Okay, and so that was done in section 1. And what else did we do? Question 8. Question 8 was done in section 1.
We did 2 questions.
Well, didn't we do question 8? Yes.
We did 3 questions.
3 questions. Okay. And so those were, I attacked the hardest of questions from this particular homework, and we'll have another chance to take a look at this homework as well for our next class, which is on Monday. And if you missed anything, I'm going to see if I can have this done as a recording, and then maybe this will be something you can review, or if you want to and you have the time, you can stay tuned in for our next class, which begins at 2 o'clock, our next exciting digital design class. So are there any questions before we sign off? We've got 25 participants here. That's really very good. Isn't that good? That's very good. So with 25 people and I don't see any questions, everybody stay safe. And I hope you like the presentation format with the iPad. And I'll see what I can do to improve things even better over the weekend. I've got a tablet on order. Thank you. Have a great day.
Bye-bye.
Bye-bye.